In this lesson, we're going to be covering continuous probability distributions, and we're going to start with the normal distribution. The normal distribution is perhaps the most important continuous probability distribution in the entire field of statistics. Its graph, called the normal curve, is the bell-shaped curve shown on the screen, which approximately describes many phenomena that occur in nature, industry, and research. For example, physical measurements in areas such as meteorological experiments, rainfall studies, and measurements of manufactured parts are often more than adequately explained with a normal distribution. In addition, errors in scientific measurements are extremely well approximated by a normal distribution. And the normal distribution is often referred to as the Gaussian distribution. The mathematical equation for the probability distribution of the normal variable depends on two parameters, mu, which is its mean, and sigma, which is its standard deviation. And hence we denote the values of the density, you can see that over here, of the normal of x, mu, sigma. So random variable x, mean mu, and sigma standard deviation. Once mu, the mean, and sigma, the standard deviation, are specified, the normal curve is completely determined. In this figure, the two curves are identical in form, but are centered at different positions along the x-axis. As it can be seen, mu1 or mean 1 of this curve is less than mean 2 or mu2 of this curve. But you can also see that the standard deviations, sigma 1 is equal to sigma 2. Okay, in this figure, there are two normal curves with the same mean, so mu1 equals mu2. Second curve is lower and wider, so the standard deviation of 2 is greater than the standard deviation of 1. And therefore, the more variable the set of observations, the lower and wider the corresponding curve will be. And just remember, the area under a probability curve must be equal to 1. Note that for a normal distribution, the mode, which is the point on the horizontal axis where the curve is at a maximum, so that would be at the center, that occurs when x equals the mean, mu. The curve is symmetric about a vertical axis through the mean, mu. The curve has its points of inflection at x equal mu plus or minus sigma. So at one standard deviation, that's the points of inflection. It is concave downward if mu minus sigma is less than x and x is less than mu plus sigma, and it's concave upward otherwise. The normal curve approaches the horizontal axis, you can see where it's doing that, asymptotically as we proceed in either direction away from the mean. The total area under the curve and above the horizontal axis is equal to 1. So this entire area is equal to 1. And this is getting very, 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 very close to the line as those two approach a negative infinity and a positive infinity. In addition to the application and reasonable approximation of scientific variables in real-life experiments, the normal distribution finds enormous application as a limiting distribution. Under certain conditions, the normal distribution provides a good continuous approximation to the binomial distribution and also to hypergeometric distribution. Now, we didn't talk about that one, but just know that normal can approximate that as well under certain conditions. This graph shows the empirical rule. And the empirical rule states that nearly all data will fall within 3 standard deviations of the mean. So if you look at this curve, the dark blue is 1 standard deviation. So from the mean 0, that's 1 standard deviation, 1 standard deviation. And about 34% of the data is on each side. So within 1 standard deviation, you can say you've got 68% of the data is within 1 standard deviation. That's a 68. And then the next shade of blue, the medium blue, is another standard deviation. So at this line from center, that's 2 standard deviations that way and 2 standard deviations that way. And the entire area encompasses, it's about 47 and a half on each side, so it's 95% is within 2 standard deviations. So if we look at this, that's 95% of your data is within 2 standard deviations. And then for the third standard deviation, it is the last light blue headed towards the tail, and that captures another 4.7% of the data, or about 99.7% of your data is within 3 standard deviations of the mean. So again, that is called the empirical rule, and you can use that in your computations pretty quickly. So you know that within 1 standard deviation, you have 68%, within 2, 95, and within 3, 99.7. And regardless of how tall or how flat your curve is, that is the rule, and that will hold. Okay, let's talk about the area under the normal curve. The curve of any continuous probability distribution or density function is constructed so that the area under the curve bounded by the 2 ordinates x equal x1 and x equal x2 equals the probability that the random variable x, so the probability that big X, it assumes a value between these two, between x1 and x2. So you can see that on the graph. So what we're looking for, what's the probability that the value falls between x1 and x2. So to do that, we would do, this is a continuous distribution, so we would have to integrate, not sum, as we did in our discrete. So we now have to integrate our normal curve, where we have x with the mean and standard deviation, and our density function. You could see it listed here, and we had that in earlier in the video. But the normal curve is dependent on the mean and the standard deviation of the distribution under investigation. The area under the curve between any 2 ordinates must then also depend on the values, the mean and standard deviation. There are many types of statistical software that can be used in calculating areas under the normal curve. However, it would be hopeless to attempt to set up separate tables for every conceivable value of mu and sigma. Fortunately, we are able to transform all the observations of any normal random variable x into a new set of observations of a normal random variable z with mean 0 and variance 1. And this can be done by means of the transformation. The z transformation formula is z is equal to x minus mu divided by sigma. And with this transformation to z, then mean is always 0 and sigma is always 1, and this will allow us to use a normal table to find our probabilities. So the distribution of a normal random variable is called, with mean 0 and variance 1, is called, the distribution of a normal random variable with mean 0 and variance 1 is called a standard normal distribution. So the original and transformed distributions are illustrated on our chart. So the curve, the shorter curve, is the normal, the original, and the taller curve is the z-curve. And you can see where it shows the mu is equal to 0 and the sigma is equal to 1. Since all the values of x falling between x1 and x2 have corresponding z-values between z1 and z2, the area under the x-curve between the ordinates x1 and x2 equals the area under the z-curve between the transformed ordinates z1 and z2. So these two shaded areas equal each other. So they're equal.